My name is Professor Orata. We are continuing with our thermodynamic lecture series. So we want to look at pressure, volume, temperature profiles for fluids. Pressure, volume, temperature, data. So that's basically what you want to look at. This is very important. It's very important in fluids. And when we're talking about fluids, I'm referring to both gas and liquids. So we normally refer in general, fluids will represent both gas and liquids. It's very important to take note of that. Now, let us start by looking at the behavior of water. And remember always that in this determining the physical properties of these fluids, like I've put there, pressure is very important. That's a very important property. Specific volume is a very important property. Remember, specific volume is the reciprocal of density, and then, of course, temperature. So if we take, for example, a cylinder, which we had worked with, remember we talked about PV work and so forth. This is a cylinder, and then we have a piston. We have a piston here, and then we have atmospheric pressure. Remember that we said that there are certain assumptions which we didn't make about pistons when we derived some earlier expressions for work in the earlier lectures. We said that this piston will assume several things: that it had no mass, it was rigid, in other words, it's not collapsible, it is perfectly fitting, so there's no leakage and so forth, and it is also, this process is frictionless, which is normally quite a challenge in practical reality. Now, if we have ice, let's say we have ice in this cylinder, and we follow the temperature profile of that ice under constant pressure, and make it your tradition to always know that to do these measurements, if you have three variables, pressure, volume, and temperature, when you're dealing with pressure, volume measurements, you keep the temperature constant. When you're dealing with pressure, temperature measurements, you keep the volume constant. When you're dealing with temperature, volume measurements, you keep pressure constant. And this goes without saying. For example, we saw that when you're dealing with components, if you have three components and you have the mole fractions, x1, x2, x3, if you know x1 and x2, you know x3 because they all must add up to 1. So it's very, very important to always know that if you define the two, if out of these three, if you define two, those variables, then you can compute the third one. And remember, in terms of fluids, they are linked up with equations of state, like the ideal gas equation of state, and the other equations of state which you mentioned, like the Van der Waals equation of state, the Beatty-Bridgman equation of state, the Barthelot equation of state, Varial equation of state, Redley-Kwong equation. There are Redley-Kwong equation of state. There are many, and so those characteristic equations are very important, and they are able to relate these particular variables in one go. So, if we have, for example, ice in this cylinder, and we change the temperature of the ice, so what are we having? We're having a temperature volume profile. Temperature volume profile. That is volume, that is temperature. For this ice in the cylinder. Now, as you heat this system up, the ice, remember the process we have here is we have the solid is the ice. We expect it to go to the liquid. Those are the phase transformations. You go to the liquid and it will go to the vapor or gas phase. And remember, these are phase transformations. This phase transformation where we have solid going to liquid is fusion, and liquid going to gas is vaporization. And there are accompanying heats of those particular processes, latent heats associated with these particular processes. In this case, solid going to liquid will be accompanied by a latent heat of fusion, sometimes called sensible heat. And here we have liquid going to gas, that will be latent heat of vaporization. Latent heat of fusion, sometimes called sensible heat. And latent heat of vaporization. And during these phase transitions, as you heat your solid ice, the temperature will increase. Let's follow our discussion with the profiling it on the temperature volume matrix. So as you heat your ice, the volume will change, will increase. Yeah, let's try to get it drawn better. The volume will increase. And then at 0 degrees centigrade, let's just mark that as 0 degrees centigrade, that process of fusion will start, or melting will start. Remember, the reverse process is freezing. So when we reach 0 degrees centigrade, it will start to melt. Now, because this is water, we mentioned in the Clapeyron equation that delta V for water, that is the change in the volume of liquid water minus that of the solid water, this is negative. Why? Because the volume of the ice is greater than that of the liquid water. So we are going to see when we reach this particular temperature where we have fusion, we are going to see that the volume decreases. The volume decreases. And that is because of that explanation there in terms of the volume of the liquid and the solid for the case of water. And then, remember now, once we go to the liquid, during this transition where we are changing from solid to liquid, the temperature is relatively constant. During the first transformation, temperature is constant. That when we are changing from solid to liquid, the temperature is constant. And we said that the heat associated with that transformation we refer to it as the latent heat of fusion or sensible heat. And then, of course, now as we continue heating, then the volume will increase. The volume will increase. The volume will increase until again we reach the boiling point, or where it vaporizes. At that point, that's vaporization. And again, the temperature will be constant. And this will again be accompanied by that process there, that is latent heat of vaporization. Remember that we said that the heat transferred under constant pressure is the same as the change in enthalpy. And that's why we talk of latent heat of vaporization, of fusion, of vaporization. So this is basically delta H fusion, and this is delta H of vaporization. And it's delta H because we're talking about heat which is being released or being absorbed during that particular process under constant pressure. And we say that this thermochemical observable heat transfer under constant pressure is that change, that heat transfer under constant pressure is the same as the change in enthalpy of the process. So we get that kind of profile, temperature constant when we have fusion. So let's mark that as fusion. And when we have vaporization, temperature again will be constant for those phase transformations. And that's very, very important to remember that. And that was a very important component when we interfaced the Carnot cycle and the Rankine cycle. They are in the other lectures which we did previously. Now, let us now look at the pressure volume profile. The pressure volume profile for a single component system or a pure substance. And I must need to mention also that, remember, I've talked of, let's talk of pressure, temperature. We said for water, that is negative because of the volumes of water, volume of liquid being less than the volume of solid. But in normal substances, this is for water. In normal substances, it is positive. In normal substances. Always bear that in mind. Because if a normal substance is positive, then remember that in that particular case, there will be no decrease in volume. In fact, we will have a new curve for the normal case, normal substances. What we are going to have is you are going to have temperature versus volume. We want to have temperature versus volume. So we are going to have that direction, that manner. That will be fusion, and that will be vaporization. This is for normal substances. For example, if you take carbon dioxide and the others, you get that normal pattern. Water's that aberration in the sense that the volume of ice is greater than that of the liquid water. That's very important to note that point. Now, let us look at the pressure volume profile. Pressure volume profile. Let us look at pressure volume profile. This is very interesting. When you look at the pressure volume profile, that is, you have the pressure, P, and you have the volume, V, the profile. Get that dome shape, and this is the saturated curve for the liquid, saturated curve for the liquid, saturated liquid curve. We have already seen this in other earlier lectures. And this is the saturated vapor curve. Saturated vapor curve. So I don't want to write the full, that's saturated. I've just shortened it. It's the saturated vapor curve, saturated liquid curve. And so we have the critical point here. The critical point. And we say that corresponds to the critical temperature. So that if you take, for example, pressure temperature profile for carbon dioxide, where we have solid, liquid, and gas, or even for water, that is carbon dioxide, CO2, and if we have for water, that will be negative. Now, this corresponds to the critical temperature. And above the critical temperature, you cannot differentiate between the liquid and the vapor phases. So that for water, it occurs at about 220 bars. 220 bars and about 650 plus Kelvin. And so it's very important to remember that above the critical temperature, you cannot differentiate between above the critical temperature, that's the critical temperature. You cannot differentiate between liquid and vapor, whether you're dealing with water, or carbon dioxide, that's the profile for carbon dioxide. And when you're dealing with water, remember, like we have said, that slope is negative, it will be that. So for water, that's about 220, the pressure is about 220 bars. For water, it corresponds about 220 bars and 650 plus Kelvin and so forth. So it's a very important point to note. Now, this critical point, that's what corresponds to this, what we call the critical point for the substance. Again, like we have said, you are not able to differentiate between the liquid and the vapor phases. Now, what does that mean? Suppose we increase the pressure. Let us say we are increasing the pressure at some temperature T1. Temperature T1. We increase the pressure. In other words, we're increasing the pressure and decreasing the volume. So we increase the pressure. We will move in that direction, increasing the pressure and a constant temperature. At a constant temperature, we reach this point where we will have a wet vapor here. That is, we will have both the vapor and the liquid phases coexisting together in equilibrium. So we'll have liquid plus vapor. Plus liquid in this region here. So here we have our gas or superheated. We have the superheated in the superheated region. We have gas. Now we have liquid plus vapor here. And here we will have, when we reach this particular point, notice that we are decreasing the pressure. We are increasing the pressure. And of course the volume is decreasing. We reach this point, the saturated vapor curve, we start having we start having liquid in the system plus vapor, that's the wet vapor. And you can talk about their dryness fractions. The dryness fraction at a state point on the liquid curve corresponds to x is equals to 1.00, and on the saturated liquid curve it corresponds to x is equals to 0.0. Let me just specify what dryness vapor is. The dryness fraction is, if you have not gone through the other earlier lectures, we discussed elements of it in the earlier lectures. We talk of dryness fraction x, that's the dryness fraction. And that is very simple. X is simply the mass of dry steam divided by mass of dry steam, vapor, plus mass of liquid. And there's also the wetness fraction. Wetness fraction is normally mass of liquid over mass of mixture. So these are some important quantities you need to know. So the dryness fraction on the saturated curve is 0. Why are we saying that? On the saturated liquid curve, we only have the liquid. We don't have steam. So we only have liquid, whatever percentage it is, it doesn't matter. But there's no steam, so that's 0, 0. You're dividing that. That would be 0. At the saturated vapor curve, we have steam. So it has a value. It's a value, but there's no, we don't have liquid. We don't have liquid there, so that is 0. So definitely it will be 1 or in the region 1. So in this particular region, what we are saying is the dryness fraction ranges from 0 to 1. Dryness fraction ranges from 0 to 1 in this particular region. So as we are increasing the pressure, when we reach this point, we start having liquid. So we have wet vapor where we have some liquid in coexisting in equilibrium with the vapor. And then, pay attention, at this particular point, when the liquid region, at this particular point, now we are compressing the liquid. We are compressing the liquid. And so you will find that that curve is very steep because you're compressing the liquid. If we choose another temperature which is slightly higher than T1, let's call it T2. So temperature T2, where T2 is greater than T1, again the whole process will be repeated. We will have liquid vapor coexisting together, and of course, again, that curve there. But now suppose we are above the critical point. I want you to take note of that. Above the critical point, you cannot isothermally compress. That's under constant temperature. You cannot compress the vapor to liquid. Above that point, you cannot compress that. So above here, above critical point, you cannot isothermal compression of vapor, of gas, or vapor to liquid. Note that above this point, you cannot compress the gas to get a liquid. Above the critical point here, above it, you cannot compress the liquid, the gas to the liquid phase. Now, all these points are being constructed. The saturated curve, the saturated liquid curve, and saturated vapor curve are constructed by taking all those and seeing the points where we have at that particular point. Like for example, if you're moving from here, if you are lowering the pressure, when you reach this particular point, there will be some vapor which will be forming, and of course their fractions will be given by those mass balance tools of dryness fraction or wetness fraction to tell you the relative amounts of these particular quantities. Now, let us look at this profile in the temperature entropy axis. That is entropy, temperature, entropy axis. Again, we have our system, but the most important point here which I want to bring out this temperature entropy system there is the element of degree degrees of superheat. That is, the degrees of superheat is the temperature above which you heat that vapor beyond its normal boiling point. For example, you remember this point here, when you are working with those circles, Rankine and the likes, this is the saturation pressure. That's the saturation pressure. So, we still have our liquid plus vapor. You have our liquid, you have our vapor. Now, remember that when you have your saturation pressure at this particular point, at this point here, you have the superheated vapor. This is the superheat region. The superheat region. Now, if the state point here, let's call it T1. The temperature of the superheated vapor here is T1. And its normal boiling point corresponds to this temperature here. Let's call it T2. That difference in temperature here, that difference here represents the degree of superheat. In other words, for example, let us say that you have liquid water and you have it in an evaporator, you are evaporating it. You are evaporating that liquid water. And the liquid water, you have liquid water, you evaporate it. Let's say liquid water, you evaporate it. And it boils at 212 degrees Fahrenheit. And Fahrenheit is a common temperature denomination or temperature unit, which is good to know, because in terms of degrees Celsius, Fahrenheit, we have degrees Fahrenheit. To get degrees Fahrenheit, just subtract 32 and multiply by 5/9. That's just a conversion from Celsius degree scale to Fahrenheit. Now, if it evaporates at 212 degrees Fahrenheit, but your superheated vapor is at a temperature, let's just call that, let's put that at a scale, is at a temperature of 213 degrees Fahrenheit. Then the superheat, okay, degree of superheat is 1 degrees Fahrenheit. So the vapor is 1 degree Fahrenheit above that of its normal boiling point. That is at the saturation pressure there, the saturation pressure. And of course, if we have that superheat region, you know that we will also have the subcooling. Let's say we are at that particular point, and we have a state point here. That's the subcooling. So very important for us to know. So some of these pressure volume profiles are very, very important in terms of understanding thermodynamics. They are very critical because the properties of the fluids, which is important in all quantitative and qualitative discussions of thermodynamics, is pressure, specific volume, and temperature. And so we have looked and seen how, for example, the ice will behave in a cylinder when you change its temperature under constant pressure. We have also seen the pressure volume profile, where when we lower the pressures, we see how we come into the wet region, where we have both liquid and vapor coexisting in equilibrium, and so forth. And then we have looked at the temperature entropy profile, where we have just mentioned the issue of the degree of superheat, which is simply the difference between the temperature of that vapor, superheated vapor, from that of its normal boiling point at the saturation pressure. And so that's very, very important. Those are very, very important quantities to always remember. So we'll pick up next in the other subsequent lectures.